Welcome back. In this section, we'll be looking at trigonometric identities. What an identity is any equation which is always a true statement, no matter what the value is for the variables. So something, for example, like this, x minus 1 equals 2x minus 2 over 2. That would be something that's an example of an identity because no matter what value you put in for x, the left side and the right side of the equation will always be equal to each other. So this is an always true statement, and if a statement is always true, it's an identity. On the other hand, something like this, x minus 1 equals 5, that would not be an identity. It's not always true for every value of x. It's only true for some values of x. This would be something that we would call a conditional statement. It's something that's only true for certain values of x, but not for all of them. And that's a lot of what we looked at in the past, having some sort of an equation where we wanted to find out what values of x solved this equation. But here in this section, we're not interested in solving for values of x. What we're interested in is showing that no matter what value of x you have, that the left side and the right side would always be equal to each other. Now, we already have a bunch of identities that we've already seen, and I'm just going to show you a few of those. We've seen before the even and odd identities. And again, these are statements that are always true statements. No matter what angle we're talking about, sine of negative theta is equal to negative sine of theta. As long as secant is defined, secant of theta and secant of negative theta would be equal to each other. So these are things that are always true statements. Also, our other identities like the reciprocal identities, the Pythagorean identities. We also had the identity that tangent could be defined as sine divided by cosine. That's another kind of an identity. Or that cotangent could be defined as cosine divided by sine. That's another identity. The whole idea here is that if we have identities, then when we get to the point where we want to solve a trigonometric equation, we can use these identities to simplify our equation before finding our values for our variables. Now, we had originally came up with the Pythagorean identities using a right triangle trig argument. But now we're just going to simplify our life here by doing the same sort of thing, proving our Pythagorean identities, but this time not starting with right triangle trigonometry, starting with the unit circle. So again, reminder that if we're talking about an angle theta, and we're thinking about that angle inside the unit circle, you'll have some point x and y, and the value for r here, if you're in a unit circle, is 1. You know that in a unit circle, x squared plus y squared is equal to 1. And that's, of course, because that's the equation of our unit circle. That's the whole point of why we're using the unit circle, because we know that that gives us a value of r being 1. But we also know that in the unit circle, that x would be the value for cosine of theta. Remember that we had defined in the unit circle that cosine of theta was the x value, so x squared is cosine squared, and the y value is sine theta, so y squared is sine squared theta. And so the reason for this, of course, is because sine theta is y and cosine theta is x in the unit circle. So we've actually established that very first Pythagorean identity, and then the other two identities we can establish in the same way that we did before. Taking that first identity, and if I were to divide everybody by sine squared, if you were to simplify that, cosine over sine is cotangent, so cosine squared over sine squared, that would be cotangent squared theta. And sine squared over sine squared is 1. 1 over sine is cosecant, so 1 over sine squared is cosecant squared theta. And there we go, we've established our second identity. And I can do the same thing with the last identity, the third identity, just by taking equation 1, cosine squared plus sine squared equals 1, and this time dividing everybody by cosine squared. So I have my cosine squared plus sine squared equals 1, and I'll divide everybody by cosine squared. And then this simplifies to give me cosine squared over cosine squared is 1. Sine over cosine is tangent, so sine squared over cosine squared is tangent squared. 1 over cosine is secant, so 1 over cosine squared, that is secant squared. And there we go. Those are all three of our identities now established. Okay, so when we're simplifying trigonometric expressions, there's a bunch of different things that we could do depending on what the expression looks like. So basically what we're doing is using the identities that we already know to help simplify these expressions. So some things that we might do could include rewriting things in terms of sines and cosines or using our reciprocal identities. So for something, for example, like this, where we have sine times secant times cotangent, I might decide to start off by saying, well, I know that secant is the same thing as the reciprocal of cosine, and cotangent is cosine divided by sine. And so we can see that actually a lot of things will cancel here. The cosine and the cosine would cancel, the sine and the sine would cancel. So actually we would be left with 1. So as it turns out, that expression that we have, sine theta, secant theta, cotangent theta, that's equal to 1 for any valid angle theta. So as long as those functions are defined, then we would have that it's always equal to 1. Maybe we need to use even or odd identities. Here, the reason why I'm thinking about using those is notice that we've got cosine of negative theta and sine of negative theta. So what I might do here, I might say to myself, well, I know for starters that cosine is an even function. So I know that cosine of negative theta is the same thing as cosine of theta. I also know that sine is an odd function, so sine of negative theta is negative sine of theta. And so I've got negative cos theta over negative sine theta, which is the same thing as positive cos theta over positive sine theta. And cosine over sine, that's cotangent. So the expression that we have simplifies to give us just cotangent of theta. Maybe we might need to use one of our Pythagorean identities. So this is something that you might think about doing if you see something like a sine squared or a tangent squared or a cosine squared. That might be an opportunity for you to use one of your Pythagorean identities. The one that I'm looking at here, I know in the denominator I have secant squared minus 1, and I'm thinking about that Pythagorean identity, tangent squared plus 1 is equal to secant squared. So in other words, I could rewrite that identity where tangent squared is the same thing as secant squared minus 1. So that's my goal here. I'm going to start out by replacing that denominator, that secant squared minus 1, with something equivalent to it, tangent squared. So I'll say that we have here tangent cubed over tangent squared. And of course, that's the same thing as just tangent of x. Maybe we might need to factor and perhaps apply some other identities. I'm looking here, and if you're looking at this expression, I mean, you could think about a bunch of different things. Maybe you might decide to turn tangent squared into sine squared over cosine squared. That's a possible way to approach things. Maybe you might decide instead to replace tangent squared with secant squared minus 1 using one of those Pythagorean identities. That's another approach you might take. But I'm going to go with the more obvious thing here, which is we have cosine theta as a common factor. So I might first just say, well, why don't I factor out cosine theta out of the two terms that we have and then see what's left over. And so when I factor cosine theta out, I'm left with tangent squared theta plus 1. And here's where I'm thinking about my Pythagorean identity. I know that tangent squared plus 1 is the same thing as secant squared. And I also know that secant is the reciprocal of cosine. So secant squared is the same thing as 1 over cosine squared. So we can do a little bit of canceling, and what we would be left with would be with 1 over cosine, which is the same thing as secant theta. So that initial expression that we have simplifies really just down to secant theta. This is something that you might want to do occasionally. If you've got a two-term expression, you could create a difference of squares. And that may be potentially helpful. The reason it might be helpful is because if you're thinking back to those Pythagorean identities, a lot of those could be rewritten as a difference of squares. So for example, you know that tangent squared plus 1 is equal to secant squared, but that could be rewritten as tangent squared minus secant squared is equal to negative 1. So in other words, if you had this difference of squares, a tangent squared minus a secant squared, you could replace that with a negative 1. And you know that you would be able to make a difference of squares if I have tangent plus secant, and if I were to multiply top and bottom by the conjugate, tangent minus secant, then we know from earlier that the denominator would be the same thing as when we have a plus b times a minus b, we're left with a squared minus b squared. And that's the idea that I'm using here. Multiplying something by its conjugate will give me first thing squared minus the second thing squared. Now, in the numerator, I'm just going to leave it for now as cosine multiplied by tangent minus secant. I'll deal with that on the next line. Okay, so we had that tangent squared minus secant squared. That was going to be equal to negative 1 using our rewritten Pythagorean identity. Again, remember that the whole reason why we were doing this was because we knew that tangent squared plus 1 was equal to secant squared, which meant that tangent squared minus secant squared would be able to be replaced with negative 1. And that's what we're going to be doing in our denominator. So the denominator is negative 1. For the numerator, I'm going to simplify my life here by first off rewriting this as cosine times tangent minus cosine times secant. And I'm going to now simplify this by rewriting tangent and secant in terms of sines and cosines. Tangent is sine over cosine. And secant is the reciprocal of cosine. And a bunch of things are going to clean up nicely for us here. I'll have that the cosine and the cosine will cancel. and the other cosine will cancel. So really what I'm left with here is sine x minus 1 over negative 1, which is the same thing as positive 1 minus sine x. And so there we go. I have now that my original expression could have been simplified down to give me just 1 minus sine x. Now, I do want to say that there are other things that you could do. This was one approach that I took to simplify this expression, but I do want to say that there are other ways that I might have tackled the same problem. I might have decided to take at my first move here to rewrite tangent and secant, perhaps in terms of sines and cosines. That might have been my first move. And then I might have decided to simplify this complex fraction by multiplying everybody top and bottom by cosine. That might have been a first move, and then I might continue on from there. So it's not that there's always only one way to proceed. Remember that any identity that you apply, if it's a valid identity, then that's a valid move to do. So that means that things like replacing tangent with sine over cosine, you can always do that. You can always replace secant with 1 over cosine. Those sorts of things are always available to us. They might not always get us to where we want, but they're always worth trying. And that, just like we had with solving exponential equations and solving logarithmic equations, how there might be more than one way to solve that problem. Same thing with simplifying trig identities. Sometimes more than one identity might apply.